Hello everyone. In this video, I'll be talking about Sn1 mechanism. You can check the previous video for Sn2 mechanism. Okay, so let's get started. Sn1 mechanism. Sn1 mechanism. So you already know that S stands for what here? Substitution. S stands for substitution. N stands for nucleophilic, right? And 1 stands for unimolecular. 1 stands for unimolecular, right? So we can assume that Sn1 mechanism is nucleophilic substitution reaction following unimolecular reaction or first order kinetics. Sn1 substitution nucleophilic unimolecular reaction, right? So as usual, you know that this particular mechanism you will mainly come across in haloalkenes chapter. So let us take one example for Sn1 mechanism, the reaction which follows Sn1 mechanism. The example what we are going to take is tertiary butyl bromide. We will take tertiary butyl bromide with what I will take? I will take the nucleophile OH minus. So for this mechanism, you can take a strong nucleophile or even you can take even a weak nucleophile like water, or you can also consider ethanol as a nucleophile. So the Sn1 mechanism, in the Sn1 mechanism, you can take a weak nucleophile like water as well as ethanol, or you can take a strong nucleophile also. Yake, you will come to know that at the last of this particular mechanism. Sn1 mechanism, weak nucleophile ತಗೋಬಹುದು, strong nucleophile ತಗೋಬಹುದು. ಯಾಕೆ ಅನ್ನೋದು last ಗೊತ್ತಾಗುತ್ತೆ, right? So here it's going to give you what? As usual, the Br is what here? The halogen, which is a weak nucleophile. It will be replaced by a stronger nucleophile. So stronger nucleophile than the halide ion. Okay. So what will be getting here? CH3, CCH3, CH3. The Br will be left, and in the place of Br we will be getting a nucleophile OH minus. So Br minus will be a leaving group here. So Br minus will be removed. So this is the equation, right? So what did we start with? We started with tertiary butyl bromide. We started with tertiary butyl bromide, and what did we get? We are going to get tertiary butyl alcohol. So this reaction is going to follow which mechanism? Sn1 mechanism. So we started with tertiary butyl bromide with a nucleophile. The halide ion will be replaced with a nucleophile to give you tertiary butyl alcohol, right? Now let us compare the same with the example that we took in Sn2 mechanism. For example, if we consider the example that we took in Sn2 mechanism, if we consider what? CH3, CH2, Br for example, right? And if we react that with OH minus, and what is that going to give us? C2H5, or we can consider CH3, yes, CH3, CH2OH. So this is the example which we took for which mechanism? Sn2 mechanism, right? And there we said that due to less steric hindrance, this is favorable by Sn2 mechanism. So considering that steric hindrance, there is a large amount of steric hindrance here. So you can say that this reaction will be extremely slow because there is large steric hindrance, and this reaction will be fast because there is a less steric hindrance here, right? So, but it is observed that if you consider tertiary butyl bromide with a substitution by a particular nucleophile, this reaction is going to be far more faster than this. This reaction, this particular reaction which we have written here, tertiary butyl bromide giving us tertiary butyl alcohol, this particular reaction is going to follow a mechanism which is going to be far faster than this particular mechanism. So that clearly means that this reaction is not going to follow Sn2 mechanism. Had this been following Sn2 mechanism, the reaction would be very slow, but this reaction is taking place extremely faster than this. So therefore, this is going to follow another mechanism than this. Okay. So therefore, this is going to be Sn2 mechanism. So now we are going to study the mechanism of this particular reaction, right? So this Sn1 mechanism, it is going to take place in two steps. Okay. So step number one is that we'll start with tertiary butyl bromide. So there will be ionization. There will be ionization of tertiary butyl bromide. There will be ionization of tertiary butyl bromide to form a carbocation. So this is the first step, right? So what happens in the first step? Ionization of what? The tertiary butyl bromide to form what? A carbocation. So let us see how does that happen. So let us consider the tertiary butyl bromide. The tertiary butyl bromide, it will be ionized, and the ionization process is going to be reversible and slow. So first step, what is happening? The tertiary butyl bromide is undergoing ionization, and that ionizes to give me what? If it ionizes, the Br will be going out, and what will be formed here? You will be left with carbon with 3 methyl groups. Carbon with 3 methyl groups. If a Br minus goes, you are left with what? C plus. This is the carbocation. Carbon carrying a positive charge. Right? So tertiary butyl bromide. Tertiary butyl bromide slowly ionizes to give you what? Tertiary butyl carbocation. Tertiary butyl carbocation is formed in the first step, right? So here you need to understand that this particular tertiary butyl bromide is undergoing ionization, and for the ionization is going to be favorable by what solvent? Polar protic solvent. Polar protic solvent has to be there. If polar protic solvent is there in this particular reaction mixture, that is going to help the ionization take place. Right? How does it help it? The protic part will solvate the bromide part and removes it out, and the polar part of the solvent will solvate the ionic part of this and separate it. So in fact, the bond between C and Br is broken with the help of polar protic solvent. So polar protic solvent, if it is there, it will help to solvate this, the living part as well as the carbocation part, and hence it will help to break it down. Only if it breaks down, we are going to get tertiary butyl carbocation and bromide. Okay? So this is first step. In the second step, what is going to happen? In the second step, and in the first step, remember, do not forget to give a positive charge on carbocation. What you do in boards is, you say that carbocation is formed, but you don't put positive charge. You're going to lose marks there. So the second step, what is going to happen? Attack of nucleophile. Attack of nucleophile on carbocation. Attack of nucleophile on carbocation. First step ಅಲ್ಲಿ ಏನು ಫಾರ್ಮ್ ಆಗಿದೆ? ಕಾರ್ಬೋಕ್ಯಾಟಯನ್ ಫಾರ್ಮ್ ಆಗಿದೆ. ಸೆಕೆಂಡ್ ಸ್ಟೆಪ್ ಅಲ್ಲಿ ಆ ಕಾರ್ಬೋಕ್ಯಾಟಯನ್ ಮೇಲೆ ನ್ಯೂಕ್ಲಿಯೋಫೈಲ್ ಅಟ್ಯಾಕ್ ಮಾಡ್ತದೆ. ರೈಟ್? ಸೊ ಯಾವ ಕಾರ್ಬೋಕ್ಯಾಟಯನ್ ಫಾರ್ಮ್ ಆಗಿದೆ ಫಸ್ಟ್ ಸ್ಟೆಪ್ ಅಲ್ಲಿ? We are having a tertiary butyl carbocation. Right? So if you look at this tertiary butyl carbocation, this carbon which is having 3 sigma bonds with the carbon, this carbon is what? sp2 hybridized. The hybridization of the carbon in the carbocation is sp2. So with sp2, all the 3 bonds will be in one plane. Right? It will be like this. This is 1 CH3, 2 CH3, 3 CH3. All the 3 CH3s are on one plane. Right? Now, that is the nature of or geometry of the carbocation to which the nucleophile is going to attack. Which is the nucleophile we have taken? OH minus. That OH minus will attack this carbocation. It can attack. This is carbocation. The OH minus can attack from front as well as from the back. Right? So, there is a possibility of the OH minus attacking from the front as well as attacking from the back. Right? So, therefore, in either ways, ಅದು ಫ್ರಂಟ್ ಅಟ್ಯಾಕ್ ಆಗಲಿ ಅಥವಾ ಬ್ಯಾಕ್ ಸೈಡ್ ಅಟ್ಯಾಕ್ ಆಗಲಿ, the OH minus is going to form a bond with carbon, and that is going to form a tertiary butyl alcohol, and this reaction is quite ionic. ಇದರ ಮೇಲೂ ಚಾರ್ಜ್ ಇದೆ, ಇದರ ಮೇಲೂ ಚಾರ್ಜ್ ಇದೆ, so therefore it takes place faster. Is that clear? Right? What is the change that you observe here? First step is slow, therefore first step will be what? First step will be rate determining step. First step is slow, and therefore it is called rate determining step. Now, in the rate determining step, which is the reactant you are having? You are having 1 mole of tertiary butyl bromide. In the rate determining step, you don't have nucleophile. The role of nucleophile in the second step, which is fast step. Fast step has nothing to do with rate determination. So, in the slow step, there is only alkyl halide. So, rate determining step, there is only alkyl halide. So, the rate is changed. The rate increases or decreases. The rate of this reaction increases or decreases only based on the concentration of tertiary butyl bromide, not on nucleophile. So, nucleophile can be, I told you that nucleophile can be weak or nucleophile can be stronger. It doesn't matter because the concentration of the nucleophile does not affect the rate of reaction, because nucleophile is not there in the first step, which is slow step. Slow step ಅಲ್ಲಿ ಯಾವ reactant ಇರ್ತಾವ, only concentration of that reactant will affect the rate of reaction. In this slow step there is tertiary butyl bromide, only that concentration will affect the rate of reaction. So therefore the Sn1 mechanism can take place with a weak nucleophile as well as a strong nucleophile. So therefore, since first step is the slow step, we are going to apply the law of mass action to slow step. Applying law of mass action to slow step. Applying law of mass action to slow step. A slow step begin with rate determining step. Okay? In that rate determining step, how many reactants are there? Only one. So therefore, the rate is directly proportional to that reactant only. Which reactant? The tertiary butyl bromide. The rate is only depending on concentration of tertiary butyl bromide. So therefore I can write rate is equal to a proportionality constant, rate constant, tertiary butyl bromide, right? So this indicates that clearly the power of tertiary butyl bromide is 1. So this means that this particular Sn1 mechanism follows first order kinetics. First order kinetics means what? It only depends on one reactant. If you increase the concentration of tertiary butyl bromide, the rate of the reaction also increases. For example, if you double it, the rate doubles. If you triple it, the rate triples. Even if you double or triple the concentration of nucleophile, that has got nothing to do with the rate of reaction. The rate of reaction is only dependent on tertiary butyl bromide, because tertiary butyl bromide is there in, only that is there in rate determining step, which is slow step. So this is all about Sn1 mechanism. And here, as far as second step is concerned, the OH minus can attack from front as well as from the back. Suppose if you have taken the reactant molecule where you are having asymmetric carbon, ಇಲ್ಲಿ asymmetric carbon ಆಗಿತ್ತಪ್ಪ ಅಂತಂದ್ರೆ OH minus ಬ್ಯಾಕ್ ಸೈಡ್ ಇಂದ ಅಟ್ಯಾಕ್ ಆದ್ರೆ ನಿಮಗೆ ಇನ್ವರ್ಟೆಡ್ ಪ್ರಾಡಕ್ಟ್ ಬರ್ತಿತ್ತು, ಫ್ರಂಟ್ ಸೈಡ್ ಇಂದ ಅಟ್ಯಾಕ್ ಆಗಿರೋದ್ರಿಂದ ನಿಮಗೆ ರಿಟೆನ್ಷನ್ ಪ್ರಾಡಕ್ಟ್ ಬರ್ತಿತ್ತು. ಸೊ ಎರಡರದ್ದು ಚಾನ್ಸ್ ಇದೆ. So OH minus can 50% attack from front also, 50% can attack from back side also. So therefore, this particular tertiary butyl alcohol 50% front side attack ಆಗಿರ್ತದ, 50% back side attack ಆಗಿರೋದ್ರಿಂದ you are going to get what? You are going to get what? Racemic mixture. ಅದಕ್ಕೇನಂತಾರ? Racemization ಅಂತಾರ. Racemization is what? Mixture of two enantiomers in equal amounts. Okay? But what you need to observe here is OH minus, we have assumed that it is going to form complete racemization. Complete racemization andre endri 50% front side attack, 50% back side attack. Andre it is going to be enantiomer. It is going to be having a pair of enantiomers, one with front side and the other one with back side attack. But what happens is, you carefully idana nodidre, this Br minus which is formed, that has not completely formed and gone. A Br minus illa irtade. The Br minus will be here only. ಇದಕ್ಕೇನಂತಾರೆ ಇಂಟಿಮೇಟ್ ಅಯಾನಿಕ್ ಪೇರ್ ಅಂತಾರೆ. ಇಂಟಿಮೇಟ್ ಅಯಾನಿಕ್ ಪೇರ್ Br ಮೈನಸ್ ಎಲ್ಲೂ ದೂರ ಹೋಗಿರೋದಿಲ್ಲ, Br ಮೈನಸ್ ಅಲ್ಲೇ ಇರ್ತದೆ. ಆ Br ಮೈನಸ್ ಅಲ್ಲೇ ಇರೋದ್ರಿಂದ the OH minus will not be able to attack from front as much as it attacks from back. Okay, because Br minus is still in the same premises. Therefore, OH minus, it looks like 50% left side attack and 50% right side attack, but actually what happens is more of attack is taking place from behind. So therefore, ಇದು complete resonization ಇರೋದಿಲ್ಲ. ನಿಮ್ಮ ಪ್ರಾಡಕ್ಟ್ ನಾಗ 50 to 70% inverted product ಇರ್ತದ, about 30 to 40% retention product ಇರ್ತದ. So therefore, ಇದಕ್ಕೇನಂತಾರ partial racemization ಅಂತ. Actually what happens? Partial racemization ಅಂತ. Is that clear? It looks like complete racemization, but most of the cases, what will happen? Partial racemization. The reason is that Br minus is still not left due to intimate ionic pair. The Br minus is still with carbocation. That makes OH minus too difficult to attack from front. So therefore, most of the attack is taking place from behind. That is the reason you are getting more inverted product, less retention product. So therefore, it's called as partial racemization. So this is all about Sn1 mechanism in the basics of Sn1 mechanism. The detailed comparison of Sn1 mechanism and Sn2 mechanism will be done in the next video. Thank you so much.